Hello, guys, students, friends, colleagues. Uh, it's very cold out here in Kashmir Valley. Snow is falling outside. The temperature is gone below 0 degree Celsius. And unfortunately, this coronavirus is again spreading at a very good rate. So my request, my advice to all of you is that you should follow strictly the SOPs. The SOPs that are time to time provided by the government for the benefit of the pupil, for the safety of the pupil. So I again request all of you to follow those SOPs and save people out there and go for vaccination and other precautionary measures that we should take place. So, in addition of this, it's our duty that we should follow these SOPs. That's a very important thing. So today I'll be talking about dual nature of matter. Probably I had talked about the dual nature of radiation, which was discussed in terms of photoelectric effect and Compton effect. So dual nature of radiation is a result of the experiments that are performed out there. When you perform the experiments like interference and diffraction, you probably have no other explanation other than that of assuming that light is a wave and two waves can superimpose with each other, and you can have constructive interference, destructive interference, and that can lead to the pattern that we observe on the screen. Either we directly observe it or we indirectly sense it using sensors. On the other hand, the radiation, when consolidated with experiments like photoelectric effect and Compton effect, the results suggest that under these circumstances, light or radiations are behaving as particles, as photons. So what radiations actually are, I think nobody knows that, but under certain circumstances it's behaving like a wave where it is allowing the two waves to superimpose, and on the other side it's uniquely taking a single position in the space where you can define the effects like photoelectric effect and Compton effect. And the result is suggesting under those cases that the radiation is probably behaving in the form of quantas, in the form of photons. So with this breakthrough in the field of physics, in the field of science out there, Broglie suggested that if radiation can have a dual nature, it can have wave nature under certain circumstances and can have particle nature in some other circumstances. The same thing should go true with the material particles, because he came up with certain suggestions like this whole universe is made of only two things. One is radiation and another is matter. And the next important thing that de Broglie put pressure on was that nature loves symmetry. So if nature loves symmetry, then if we are finding some uniquely defined nature of light under certain circumstances behaving like a wave, and under some other circumstances behaving like particle, the same story can be true for material particles. The material particles here are probably the microscopic particles like electrons, protons, atoms, molecules, neutrons. So these material particles should also have the dual nature. So this is what was suggested by Louis de Broglie. So what this de Broglie equation is basically is that if you assume that there is a photon, this photon has an energy E, and this energy is equal to h nu, where h is the Planck's constant and nu is the frequency of the photon. And if this photon has the energy equal to h nu, and at the same time, if we take a moving photon, then according to Einstein, the energy of the moving photon, which has mass probably, is mc squared. So the photon, this is the Max Planck's equation, E is equal to h nu, and we can probably write for the same photon if we assume that the photon has the mass, because a moving photon has a mass. So then we can say this energy is equal to mc squared. If we equate these two equations, what we are going to get out of that is that this h nu must be equal to mc squared. Now, writing down nu here, so h will be c by lambda equals mc squared. So you can take off this c and square from this side. So what will we get? H by lambda is mc. So h is the Planck's constant, lambda is the wavelength of the photon, and m is the mass of the photon, and c is the speed of light. And if we write down this lambda, if we write down this lambda here, this lambda will be h by mc. So if we take this, if we replace this photon with a moving microscopic particle, if we take this photon and replace it by a particle, then a particle in motion, and let the speed of the particle is v, and let m be the mass of that particle. Okay, let me write mass of that particle, mp. So in that case, lambda will be h by mpv. So this equation that's out here, this equation is known as de Broglie's equation. And this de Broglie equation is telling us that the wavelength of a material particle is equal to the Planck's constant divided by the momentum of that particle. So this momentum is basically taking the situation towards the particle. So a wavelength is associated with a material particle. So lambda comes out to be h by mv. Now, if we further take this equation to some other circumstances involving some other physical quantities, we can assume that suppose Ek is the kinetic energy of the material particle. If Ek is the kinetic energy of the material particle, we can write this is 1/2 of mv squared. So Ek can be written as p squared divided by 2m, where this p is nothing but the momentum of the material particle, which is equal to the product of mass of the particle and velocity of that particle. Okay, I had chosen a subscript here as mp for the mass of this particle. So mass of this particle. So if I use this equation, this equation in de Broglie's equation, what will I get? I can write here this momentum is under root of twice mp ek. Okay, this mp is the mass of the particle and ek is the kinetic energy of this particle which is in motion. So I can substitute this momentum in the de Broglie equation. If I do that, what will I get? I will get lambda is h by under root of 2mp ek. Or I should say, the wavelength of this particle has a relation with its kinetic energy. That means I can say this wavelength is inversely proportional to the root of kinetic energy of this material particle. So this is the dependence of wavelength of this material particle with the kinetic energy of this particle. And if you go back to this equation is lambda is h by mv. You can see here, this Planck's constant is very, very small. It's extremely small. It's of the order of 10 raised power minus 34 joule per second. This is very small. And you see, the denominator is a multiplication of mass and velocity. That means, if the mass is large, then the wavelength will be very small. That means, for macroscopic bodies like this duster or a pen or a ball, in these cases, the wavelength will be very, very small. The measured wavelength will be extremely small. So it can be assumed that de Broglie equation is not valid for macroscopic objects because the value that will be calculated from this equation here will come out to be very, very small. So when this lambda becomes appreciable, this lambda becomes appreciable only when you go down to the microscopic particles. When you move down to the microscopic particles like electrons, atoms, molecules, protons. So in that case, you have a very appreciable amount of wavelength that you can measure from this equation. So the point is clear here that this de Broglie wavelength is measurable. It is measurable for microscopic particles and probably it is immeasurable. We can rule it out. It does not exist at all when you talk about macroscopic objects, macroscopic bodies. So here we have seen that this wavelength comes out to be dependent on the kinetic energy of the moving particle. That means it has wavelength, and this wavelength can be measured as an inverse of its kinetic energy. Okay, if we take this energy, average energy, we should say, we can also write it as 3 by 2 kT. So this E is the average energy. This is the classical average energy. It has a dependence on the Boltzmann constant and the temperature. In this case, this average energy is 3 by 2 kT. We can replace this energy from the equation that we have already arrived for lambda. What was that? That was h divided by under root of twice mp. Then there was ek. So instead of ek, I will write down this average energy. What will be that? That will be 3 by 2 kT. You can see this 2 and 2 will cancel. And you will get lambda, again, here, h by under root of thrice mp kT. In this equation, you can see h is a Planck's constant everything is a number here except the temperature. So the wavelength of this material particle is inversely proportional to the root of temperature. So this is the dependence of wavelength. So that means wavelength is not a quantity that is absolutely having some absolute value. It does have different values under different circumstances. The wavelength of the same particle can be having value x when it has some kinetic energy, and it will have a value y when it has some other kinetic energy. And the same will be the case with the temperature. So if your temperature is different and you are measuring the wavelength of that particle, the wavelength is not going to be same. It's going to have some average value at that point of temperature. Now, suppose this material particle, this microscopic particle, moves in some electric field having potential difference. In that case, the kinetic energy, Ek, will be EV, where E is the charge of that material particle if you are assuming it to be an electron or a proton, and V is the potential difference. So you can replace the kinetic energy by EV, provided your electron is moving in some potential difference. So the electron will be accelerated in that potential difference. So what's going to happen? Your lambda will come out to be h by under root of, was that 2mp, and instead of Ek, I will write EV. And this lambda will be h divided by under root of twice me mp, probably mass of this particle, E is the charge and V is the potential difference. So lambda will be inversely proportional to under root of V. So the wavelength of this material particle is also going to change. It will have some particular value in some potential difference. When it is 10 volts, it will have some value. When it's 20 volts, it will have some value. When it's 30 volts, it will have some other value. So that's why this wavelength is found to be inversely proportional to the potential difference. And you can see in this equation, h is a constant, 2 is a constant, mass is a constant, charge is a constant. When you boil down these constants, when you calculate all of these constants, you write down this lambda comes out to be 12.2 divided by under root of V angstroms. So you can calculate the wavelength of the particle when you have some voltage, some specific voltage at which that particle is moving. The case can be true for an electron. Electrons are generally available. They are freely available. So if you have electrons moving in some potential difference, you can measure out the wavelength associated with these electrons, with these material particles.